Happy Tuesday. Welcome back. After holiday, 1 week off. Had fun. Made lots of sculpture. Beautiful ice works. Okay, so today, what we're going to cover. So we are in random variables. Last class we talked about random variables and discrete and continuous random variables. Today, actually this week, we're going to cover these topics in general. Module 6 is for this week. Curious if I only did 6. So we're going to talk about family of random variables.
Just doing hand calculate.
Sometimes we can make a template for random variables. Some talk about that. Identify common families of discrete random variables. So you're going to learn how to select an appropriate random variable. Like Bernoulli, we're going to talk about Bernoulli this week. Today, actually, we're going to talk about Bernoulli. We're going to talk about binomial. You already know what's that. We're going to talk about geometric and discrete uniform random variables. Mostly we are working with discrete random variables this week. Continuous is going to be next week. And what else? Something interesting. We're going to see how we can find expected value or mean as some parameters and variance. How we can measure actually a spread of variables, like the random variables, how they are spread around the mean. That's a very interesting point. We call it variance, and later when we go to higher dimension, we call it covariance. We're going to see how we can compute that. That's very interesting to see how we can measure a spread of something. You know? Like, how it's changing around the mean. So we can talk about that, and we're going to learn how to use these topics in engineering. Like, for example, for networking, for sensor detection, for reliability, and lots of applications of these topics. You're going to learn those in this module or in this week. And and how this experience can share the same actually probability model that comes from the family of distribution. We're mostly going to talk about the family of distribution and random variables. Let's do some recap from last week's, like 2 weeks ago. We already know what is random variable. Random outcomes need to actually assign with numbers. Why we assign them with numbers? Because the reason is that you can do mathematical operation on them. So the points of this class is kind of modeling real phenomena that mostly are random. So we need to assign them numbers. How? Using random variables. So random variables is kind of assigning number to each outcome. We already know that. We explained last class. So the point is to mathematically play with these random outcomes. That's why we assign them numbers. So that's the point. We already know. So for example, instead of saying head and tail for coin flipping, we can call it 1 and 0. You know, we just assign a number. That number and that variable called a random variable. Okay, that's important to know. Like, for example, in sensing, for example, you are working with a sensor in a robot detecting surrounding or observing things or detecting things, for example. You can define a variable for detection. Say, okay, X is 1. If it detects at all, if not, 0. So that variable kind of explaining how this sensor works. So because it's random, we call it random variable. Why is random? Because it's not certain. The sensor is not always working fine. Sometimes working good, sometimes not. So we need to study these variables, and that's random variable. Okay? So generally, random variables can be divided to two parts. We explained last class. Discrete random variables, when actually you have actually a countable set of random variables. You can count them. You know, if the random variables are countable, that random variable is actually a discrete random variable. For example, when you are actually flipping a coin with a limited outcome. So that's actually discrete random variables. So finite or countable outcomes. Discrete random variables can be described with the function that we call it probability mass function. So probability mass function is actually tell us how probability is distributed among these values. So we call it the capital P of capital X is small x. X is that outcome. Or sometimes we put like that. P of X, capital X, is a function that you can find it. Base of different, family of random variables, different distribution. We have different functions for it. But we show them like that. So this is for discrete random variables. You're working with discrete random variables today. And continuous is with actually f of x. We're going to see that. So anyway, probability mass function is showing how this probability distributed among these possible values of x. Let's clean this up. For example, for discrete random variables like number of bit errors in a packet, if you are sending a packet in a network, you might have some error in the packet, but these numbers are limited. They're not infinite, so it's number. When it's number, you can count it, so it's countable, so it's discrete. Another example, like number of successful transmission, we are sending, again, data in networking and sending information in like transporter. Most of the time you are dealing with discrete random variables. So discrete random variables, because it's still random. Why is random? Sometimes it's going to destination, sometimes not. It has some probability to receive or not. So that's why it's random, but it's countable. You can find the number of successful or not, or just a normal, actually, dice. When you are doing that, it has limited number of values between 1 and 6, for example. That's discrete random variable. Also, we covered a little bit. We talk about continuous random variables that we're going to see later on in this class. Continuous random variables are a little tricky, and because the values are actually continuous interval. So you can't count them. There is always something between. So that's a continuous random variable. Like infinitely possible values you can find. To describe continuous random variables, you are using probability density function. That was probability mass function. That is probability density function. The difference is in probability density function, you describe probability is how probability distributed over a continuous range of values. So here you have the possible values. Here is a range of values. That's why here you can find, for example, probability of x is equal to 1, for example, is a number. You can find, for example, is 0.2. But f of x is equal to 1 is always 0. You can't find probability of one given values in actually probability density function, because there's so many things between that. You can't find it. You need to find the interval for that. We're going to see that later. But just know this part for now. Okay, so the range of value, that's where we are saying range of. We can say, okay, if it's x, we can say something like, if it's x between, for example, 0.9 to 1, this is computable. You can say this is 0.2. Between this. Okay? But we can say exactly 2. Okay, that's important part. So we're going to see that later. Example of continuous random variables, you can see them a lot in electrical and computer engineering. And nature is mostly continuous, and like a noise voltage. The voltage, if you say, okay, is this computer working in 5 volts? It's not always 5 volts, 5 and a little higher and less, And you can find exact, always you can find a little noise between. So for example, if you say it's 0.3 volts, it can be, say, okay, 0.3001 or 0.3 or 2 maybe say 2.999 volts. So we are kind of truncating that. We are kind of actually fitting that in 3 volt, but it's not exactly 3 volt. That's why it is considered the voltage like a continuous. Or, for example, arrival time. For time is also the same. When you say, for example, the time is, for example, 2 seconds, it can be 2 seconds and a little more or less, And for other, like sensor measurements, where you are measuring distance or whatever, you always have some noise that is not really countable. It can be infinite numbers between that. That type of variables are a little tricky. We're going to see them later. Any question about that? Okay, we already talked about random variables last class. But today we want to talk about a family of random variables. Sometimes it's easier to talk about a general or a template for random variables. Like, for example, say, okay, a general random variable that just have 2 outcomes can be set in this group, for example. So we call them a family of random variables. So a family of random variables is not a single experience, it's a template for many experiences that act similar to that. Okay, so we're going to see them soon. Let us clean this up. So it's just a template of many random variables in one structure. So they need to have some properties. If we call them as a family of random variables, they need to have the same probability mass function. Probability mass function is the same, but with different parameters. So random, actually probability mass functions sometimes have some parameters, like for example, P, N, or range, or whatever. Some parameters are changing. That's actually specify which random variable is that, based on which parameter. Okay. Okay, so once you learn the family, you don't need to relearn probability from scratch. You just plug new parameters. So let's see some examples. In obstacle detection, for example, for a sensor, any sensor can go set in this kind of family of random variables. You know, for obstacle detection, you have detecting the object or obstacle, for example. You can define a random variable like x, that is 1 when we detect the object, and 0 when we can detect the object. And P is the probability of detecting the object. So P is that parameter that I mentioned. So we can find a family of random variables for just obstacle detection, for example. They have all same probability like this. We have some similar probability mass function. Anybody can find the probability mass function for this? What is probability mass function? Probability mass function is a function, we call it P of x is given x, that describes so how we can distribute probability around the x. You know, we say, okay, x can be 2 values. If x is 1, what is the probability if the x is 1? We mentioned probability the sensor detect is P. Okay, so this is P. And if x is not 1, this is 0, what is the probability in this case? Any idea? What? Not P, how we can, yes, it's not P, but how we can mention that, because it's complement property, 1 minus P. 1 minus P, we are talking with numbers, you know, because the overall going to be 1, so if it's this P, this is 1 minus P. Or this is a small lowercase p. So this is all of this family of obstacle detection. They have similar actually probability mass function. Why is probability mass function? Because it's discrete. The x can be 1 and 0. It's very simplest random variable that you can imagine is this one. Later we can call this Bernoulli. You're going to see that. It's good for gambling. This actually created by Bernoulli. So you can win or lose. If you win with probability of P, you're going to lose with probability of 1 minus P. So that's simple. So that's a probability mass function. So, and you can put this structure for so many things. For example, that's called Bernoulli anyway. For example, for LiDAR, for camera, you can use it. For, you know, indoor, outdoor, doesn't matter. You can just change the speed. Those parameters can change, but the family of random variable is using for all of them. For, doesn't matter if your sensor is cheap or expensive, still just this P gonna change. And same math, different P. Any question about this? showing a family of random variables that actually make a broad applications for so many things. Just you need to change those parameters. So family of random variable, they all have same PMF, probability mass function, like this. Just parameters changing. This P is a parameter. Sometimes it's just one, sometimes more. You can see like more complex probability mass functions. Okay, so this was good. Now we want to talk about something even better. Moment. Not this moment in general. Moment. We can define moment. In probability, moment has some specific definition. Moment is a numerical quantity that summarizes how random variables behave. So random variables are random. So if it's random, how you can specify another number to summarize it? You know, for example, you are actually, let's do this example. Imagine we have a radar. Imagine it's a radar, it's a satellite, and measuring a drone, for example. Localizing a drone. So this is satellite sending some wave and try to see where is this object, if there is any, maybe not, okay? So send some signals and receive some signals and detect, there is some obstacle around it. But it gets some let's make this also a point. But because this drone is moving and this system or this satellite is not very precise, it's going to get many actually measurements. These measurements, we don't know which one is the real. But which one is the closest to real? You tell me. You get, for example, 10 numbers, 10 position. Which one is closest to the real one?
Probably the one in the center.
One
in the center, probably?
Center? Yes. Or maybe we call it mean. Yeah. Okay, centroid, not generally centroid. Or even maybe centroid is not one of the measurements. We just can say, okay, maybe this one is closest to the real, because we get lots of measurements. Which one should be? Mean. We just get mean. So mean is one of the moments. It's actually first moment. So the moment is numerical quantity that explains, summarizes random variables. Random variables are random. How you can put a number for them with these moments, with these values that we call them moments. So moments are a numerical quantity that specify, that describe random variables. One of them is this. We have so many moments. Moments 1, moment 2, moment 3. We're going to see them later. Today we're just going to see 2 of them. Mean, moment 1, and a spread or variance, moment 2. Okay, so that example actually explains. So the moment is this. So let's see more information about moment. It captures information about the distribution as a whole. You know, you get lots of things. But as a whole, you can actually get some information from all of them. So when you are computing the mean, you are getting one number out, but from the whole, the system, you get that out. So that's called the moment. It has some features. like for example, showing the trend. For example, in that case, showing the location of real drone gonna be in that red points. So it has some, and also describe some spread across the that possible value. So how you can say, okay, this is the spread of this random variable. So normally when you want to measure this spread, you are measuring distance, isn't it? You're measuring distance of all and get average of those to see how this is spreading. If this spreading is too much, it means your measurements is kind of not precise. It's loss of uncertainty. We call it uncertainty. Like for example, you have two radar, for example. One of them give you this, and the other one give this information. Is much higher. So this is another radar, and this gives you more spread. So which one is better? The one with lower uncertainty. Which one? The red. So this is showing how we can model these random variables with some numerical quantity. One of them was mean, that is a centroid. Maybe in both of these two cases, centroids be very close to each other. But because the spread in this case is a lot, you can make decision with higher certain, with higher probability. You have very low probability to say, okay. In this case, you say, okay, center is here with like 80%. For in this case, you're saying, like a drone is in this position with 50%. And you want to make a system to, shoot that drone, for example. So how you can trust. So you need to have one system or multiple of them to bring this spread smaller and smaller to can make better decision. Later we can see how we can fuse multiple, and like that to make uncertainty even less. You will see that later. Very interesting. Okay. Even in these two cases, if we fuse these two, even though one of them has lots of noise or whatever, after fusing these two, the overall is going to be smaller than each, This is very important point. We can see, we can prove it later. This is the fusion case. It's going to be smaller. Even though one of them is so big, after fusing these two, you're going to get better, actually, precision. So we can prove that later. Okay, that's the moment. What else we can say about moments? Sometimes we can compute moments using just probability mass function and random variable. We can compute that. If you have probability mass function, we can compute that. Like for the example that we mentioned before, we said probability mass function for the sensor detection. Remember? That was 1 with probability of p and 0 with probability of 1 minus p. Okay? Or maybe I write it if x is equal to 1 and 1 minus p if x is equal to 0, okay? So imagine you want to find mean for this. How we can compute mean? We said we can compute moments based off probability mass function. So we just need to make average. How we can make average? Any idea? How we can make average? We have two cases, 1 and 0, and probability 1 minus p. Because it's two cases, finding average, we just need to add them up. But we have some values here, so we can multiply these values by p and add them up. And the overall going to be the mean. So the mean, the notation that we are using for mean is E. E of x. E of x is actually x. E of x, but for all cases that happening for x. So if we add this together, it's going to be 1 multiply p plus 0 multiply 1 minus p. So it's going to be just p. This is how we compute mean. Yes?
Does the E of x notation have a different implication than x bar or mu?
Yes, same, yes.
Okay.
Yes. We showed that with x bar too, yeah. Yes, different notations, yes, that's why, yeah. So, yeah, we have different notations for them, of course, yeah. One of the notations is x bar. That's also used for mean too, yeah. Here we use E because it's expected value. Also expected value, we call them mean too. Average too, same, yeah. Okay. We're going to see that more later, so let's clean this up. Any more questions? Okay, so different moments capture different characteristics, as we mentioned. Some describe the centroid, some explain the spread of these variables. Some even explain more, you know, like for example, so right now we are just explaining two moments, moment 1 and moment, actually no, moment 0 and moment 1. I think moment 0 is, I'm not sure, they have numbers anyway. These moments explain so many information about these random variables. Central, spread, even more. Like sometimes you can see from moments, like the information that you have is like is not even centroid. Your LiDAR, for example, this happens a lot in LiDAR. LiDAR gives pointy data, and sometimes you get some information like this, and you want to study what is this shape, what is the centroid, what is the direction. Even you can get which direction this is moving. For example, this is an airplane. Even with computing moments, you can get centroid, you can get how is it spreading, and also you can see which direction is moving. We can see that later with higher moments. Some moments show you which part is like more central, most of data is in which way, or which direction is like nose. You know. We can see that later. So lots of information coming out from the moments. That's why and they are all numbers. But those numbers explain so many things. Explain you the center, how is it splitting, what is the direction, which part is, more information in some part and less information to the other side. We call it a skewing, which part is skewed, something like that. We can talk that later. Let's see the first moment. Expected value is the first moment. As I explained, we sometimes call it average. Typical value as well. So the first, that's the first moment. So we explain where is the distribution centered. In that example that we talk about, the drone, for example, detection, you might get lots of noisy information, and the centroid of that can be considered as an expected value. It makes sense, that it should be closer to the reality. We don't know reality, okay? We are just looking for that. Most of the time, reality is something that does not exist. And we need to kind of be as close as possible to the reality. So these moments give you those parameters to decide which one is more true value. Sometimes reality, we call it true value as well. Okay, so that's the mean. Where is the distribution centered? In two-dimensional space like that, is easier to imagine. Sometimes dimension is going higher. Like in one dimension also is possible. So in one dimension, you have probability and random variable x. Okay, so for different values of random variable, we are talking about discrete form. So we need to consider that. For example, this can be 0, 1, 2, 3, 4. You can have different values. Okay, and when we add them up with these values, for example, this is, I don't know, 0.3, this is 0.5, for example. We add them together and kind of weighted average, weighted sum. Average is weighted sum, isn't it? We are doing the same thing. We know these values, and we multiply them together, add them up. The value is going to be a number. The value is an average. That is just a number. For example, average in this example is going to be around here, for example. This is expected value of x. Something in two dimension is like that. In one dimension, sorry. In two dimension is like this. In two dimension is you have x and y, both random variables. X and y are both random variables, and this direction is probability. So how we show that with intensity. For example, centroid has higher intensity. Like these intensities is like a 3D shape. Something like that. Like intensity. Because intensity is around the mean more. So that if we show that with colors, for example, intensity of colors, around the centroid you have higher intensity. We're going to see later on better picture of that in 3D dimension. Even though it's two random variables, you have 3D because one of them is probability. You add one probability. That's why you have an axis as a probability. Here you have one dimension, what you show in two dimension, one is probability. Very simple too. But any question about this? It's just, I want to give you a general idea what's going on. And we're going to study them with more details later. Okay, that's the first moment. So the first moment is just centroid. Very easy to compute. You just need to, in this class, we call that E, expected value, but sometimes different notation, as you mentioned, X bar also can be used. And is equal to sum of, this dated sum of X, for all values of X. So in this case, it can be 0 X is equal to 0 multiply 0.3 plus 1 multiply 0.5 plus all the rest. I don't have the value, so I do. Okay, and then the output is just one number, and here is, for example, 1.7. Okay, this example. I'm not sure. I just draw that, but it looked like, it looked like, because it need to be close to this because of this big one. When they add them together, it should be somewhere around this. Maybe after 2, I'm not sure. We need to have real numbers to decide, but I just draw it. So we see how we compute expected value. Expected value is a centroid of the object. Kind of, if you are, you want to sense it, or a tangible, if you want to visualize it, imagine your random variables are like a cloud of points, and those cloud of points coming from some sensors that is not certain, and the centroid can be computed using expected value. Centroid of that. Sometimes centroid is so important for us because centroid is just a number or two numbers. If it's 2D or 3D, 3 numbers, you can easily make decision based off that. Sometimes not very good. For example, if it's a big ship, centroid is, because new sensors give you lots of information about the target. Sometimes you need to know shape of the target, not just centroid. So shape of the target can be studied with higher moments, higher degree of moments. Okay, what else we can say about first moment? Yes, how we can compute that? You need to repeat experiment. With just 2 experiments, for example, you really not very certain to find mean. If you have 3, it's easier to find mean, It's like making consensus. You want to, everybody agree in something. You need to have more than 3 nodes to do that, It's like voting, You want to make a decision. If it's just 2, you can make proper decision. At least need to be 3. So 3 nodes. When you make the mean, you can find a mean in between, something like that. But if it's 2, you're going to find something here, but this is lots of variety. Is not very certain. It's called consensus. Later, we can see how we can do consensus. very important part in computer. How we make decision that everybody agree with that. How we make decision that everybody agree with that. Maybe that decision is good for you, but what about others? Like you as a computer engineer or electrical, imagine you are designing autonomous system, like autonomous car, that need to make decision in intersection by itself. Can you imagine this car going to intersection and so many other, we call them agents, around. So the car, this is your car, gonna go, for example, here, for example, oh, sorry, this is not supposed to be. There is 2 lines, and your car is here, wants to turn here. Right? Yeah, they're right. Okay. And there is another car here that wants to go this way. I want to see how the complex is going to be. And there is another car here that this is also going here. And in the future, cars not to stop. Because everything is autonomous. Everything is, they just collaborate to each other. They talk to each other. Say, okay, where you go? Say, I'm going this way. The other go. Okay. They adjust their trajectory. They adjust their path to not collide, to not make collision, to make accident. And you need to do something like that, And so this is something that is very, very important. And this is consensus. At least there need to be 3 to all agree with something. They all need to agree. If just 2 of these agree, what about the other one? They all need to agree. They need to send information to each other. Like, this is Bayesian models. We can see how we can solve that in this class, in a very simple way, of course. It can be complex. That's consensus. This is consensus. Okay, we need at least 3 to make proper decision. So this is the first moment. Example, average number of bit errors per packet. When you are in a network, you're sending information using packets. Packets, they have address, they have some noise detection methods inside, parity check, when the packet going to destination, by checking that, you can see this packet, why this is yellow? Oh, it's supposed to, orange. Recording. Anyway. Normally need to be green. Yeah, okay, so average number of bits, that's one of the example. Average sensor reading, okay? So average sensor reading was that example that I mentioned. Like sensor reading give you lots of data. What is the centroid? The mean, or the expected value. Okay, that's another example. Let's show another color like this. And average waiting time for a response. Waiting time is something interesting that we're going to see that later. Next class. Waiting time is also random. And how we can, when we have multiple waiting time, you need to see average. Like it's like a customer service. Some people coming and get service right away. Some people coming, they wait multiple seconds or minutes. we add them up together and find the average. That's normal. And then we can study that distribution for that. Okay, and then we can say, okay, the distribution of waiting time for this queue or this system is this much with these parameters. You know, this is why we are here. We are here for modeling. We want to mathematically study some real systems. Why? To predict, maybe predict, okay, are you going to go to this queue? We want you not waste your time. So you can decide which time to go or how to go. And if you want to go, there is a possibility if you waste your time 2 minutes. Are you okay to go? You know, it gives you information. When you have information, you don't have anxiety. You don't have a stress. Information is everything in this world. If that guy and this guy wake up, maybe it's gonna be better. Still people are sleeping.
Early in the morning.
Yes. Okay, good. That's fine. Yes, that's important things I mentioned here. So even though individual outcomes are random, mean is predictable. You know, you're sampling so many times, you get multiple numbers. Those numbers not predictable because they are random, but average is predictable. That's why it gives you lots of information. So the average, or in general, moments are predictable. Because to measure them, sometimes even you don't need to do sample. Sometimes you just use probability mass function to compute that, like last slide example. Okay, so second moment. That's important, very important. How we can measure spread, uncertainty. How measure uncertainty? How measure variance? We call it variance. When we go higher dimension, we call it covariance. It is showing how these values spread around the mean. Okay? So we already know mean, where is expected value or mean. So let's go to that example of radar or LiDAR, whatever, sensor, and a mean that is expected value of x. Okay? We want to see how they are spreading around the mean. Easy. We just need to find the distance to mean and make another mean of that. Like we make E, expected value of x minus E of x, and find expected that. But because we want to have positive values, we do a square of this. We do a square of this distance to make it positive. And with a squaring, we are kind of give more weight to points that are far, you know. Later we can see that sometimes instead of a square, we can use, for example, actually absolute value. That's another definition, but we're going to see that later. But here, if we talk about second moment is a square. Why a square? Because we want to work with positive numbers. We want to add positive numbers. If it's positive and negative, they can cancel out each other, and we know that we're not going to get a proper result. So expected value is that. That's the equation for expected value. In that example, you can see we find the distance of each point to the centroid, and we square it, and then do another average. That's why we have another E here. We do another average. We add them together, or we weighted sum them together, okay? So it is showing how much uncertainty or fluctuation exists. Okay? So that's the second order or variance. A small variance, let's clean this up. A small variance means outcomes are very clustered and tightly clustered, and showing that, for example, if it's coming from a sensor, that sensor is very precise, reliable. And for large variance, showing more uncertain, noisy, and not reliable, and unpredictable. So that's the difference between different variants. We saw that in that example of radar, when you had higher variance, you have multiple, variety of areas that you can make decision properly. For example, two sensors may have the same average, but different variance. We saw that in that example, You can have same average in this LiDAR detection, but average is the same or very close, but a spread is different. So if this is stable, this variance is smaller, like the green one, and the wind is noisy and high variance and not stable, like the blue one. Okay, so it's that cube. Let's do this example. There is the I click, okay, I need to. That please is a robot camera check. We are checking a stop sign with camera. For example, you have a camera in the car to detect a stop sign, and the camera either detect or not. We can define a variable like x for that. I'm asking about x. X has a value that can be 0 and 1. The number of detection is multiple trial. X is the number of detection in multiple trial. The number of attempts until detection. X is a uniformly chosen value between 0 and 1. Which one is the best answer? Okay. A, that is correct. Some say B and E, but A is the correct one. Yes. This is the simplest family of random variables that I explained actually earlier in this class. It has just two possibilities, and x can be 0 and 1 with detection probability of p, and not detection 1 minus p. That's the simplest case. Yeah, so that's correct. The first one is correct, and 54 people did that. Thank you. Okay, so let's close this. Okay, why I mentioned this? Because and this. Because I want to talk about Bernoulli random variable. That was a Bernoulli random variable. Bernoulli was, Jacob Bernoulli was a Swiss mathematician, And he was studying in, of course, gambling. And that time was so many people interested to study gambling to make some more, I don't know, monies or whatever. But not any gambling, the gambling that are mostly two choices, yes or no, win or lose, you know, success or failure. This kind of studying was what Bernoulli was interested in. So he studied that and he realized, oh, many real-world experiments actually boil down to just one trial, win or lose. If you lose, you go home. You don't have more money to lose. So, and each trial has only two possible outcomes, win or lose, or a success and failure. And the outcome is not certain. You don't know, are you losing or winning? Uncertain. But probability stay the same. Probability stay same every time. You know, for example, probability of winning or losing is that P that we talk about. So that's a family of random variables that are called Bernoulli random variables. A family of random variables that has these characteristics, like they have two possible choices, the probability stay the same every time. This is called Bernoulli random variable. That's the simplest random variable ever you can imagine. But it's come from Jacob Bernoulli. 1600. Okay, so let's see what is that. This random variable, as we already talked about, has two outcomes, success, that we consider that 1, and failure, we consider that 0, with probability of P, and 1 minus P. Why 1 minus P? Because it's a random variable and need to add up to 1. And we always need to consider that for random variables. This is coming from probability axioms, remember? When we add them together, we need to get 1. If the probability of success is P, probability of failure is 1 minus P. Negate of P, as you said. And parameters, we have probability of success is P, and x can be 0 and 1. If you want to draw it, it's going to be something like that. This is for the case that this parameter P is 0.6, for example. Probability of being 1 is 0.6. Probability of failure is 0.4. Why? Because when you add them together, the space in this area need to be 1. Okay? So examples like flipping a coin. Of course, flipping a coin, if it's even coin, this P is 0.5, isn't it? But if it's not even coin, it might be, for example, 0.6 for tail, for example, or 0.4 for head. We can design that. Another example is like transmitting or transmission, like a data transmission. Single transmission bit, we can say, okay, if the error happened or not error happened, we can find the probability of that. And it has two choices, failure and success. So it's a Bernoulli random variable. Another example is like a sensor detection that we had them a lot at the beginning of this class. Let us study moments of that. Moment of Bernoulli for measuring expected value is a simple. We already computed that last second slide maybe. So expected value from that, x can be 0 and 1. And p of x can be p or 1 minus p. If we add them together, it's going to be coming from Bernoulli. But what about variance? Okay, to compute variance, we need to consider some stuff. So we said variance is say variance of x is equal to expected value of x minus expected value of x whole square. Okay, we know that before. It's because it's the distance with all x's from the mean, and we square that because we want to be positive, and then do another average. We know that, okay? Now we need to expand this so we can expand this. This is going to be e of x squared, 2x e of x plus e of x, all of that e, and then we can bring e inside. It's going to be e of x squared minus 2 of e of x, because e of, okay, this is important. E of x is what? Anybody can help me with that? E of x is a constant. Expected value of constant is what? Same. It's not changing. Expected value of constant is again same. So e of x is e of x. This is something that you need to consider in this computation. So that's why here, when I actually expand e inside this, e of x is e of x. Okay? So based off that, minus here too, e of x2 is going to be e of x2. It's not going to change that. E of x squared, because that's the number again. Oh, it's plus. So if we measure this, it's going to be e of, because e of x2, this and this going to cancel out each other. One of them going to stay, e of x whole square. So that formula that I wrote here coming from that computation. Okay? So the rest is, another thing that we need to know is that because for Bernoulli random variable, we just have 0 and 1, x squared is equal to x. Because a square of 1 is 1, a square of 0 is 0. So x squared is also equal to x. We put x in this. And we also know e of x from e of x was p. Remember, we already compute here. So we put that here, and the value is going to be p 1 minus p. So the main part was that one, that we computed this, and the rest was just we put p and 1 minus p inside, and we factor it out. Like that. Okay, let's do just one example and wrap it up. Suppose we send a bit across a noisy channel. Probability of error is 0.02, and probability of success or not error is 0.98, of course, because it's 1 minus that. And that's a Bernoulli because we have x, that is 1, that is error, and 0, that is not error. Okay? Let's find expected value. What is expected value? Expected value is a p. We know p. And what is variance is p multiply 1 minus p, 0.02 multiply 0.98. So this means the mean is this value, and a spread around the mean is like this much. That's showing how certain is this system. This system that is sending a bit, transmitting a bit, and we have possibility of error like 2%. So this variance is like that, showing how uncertain is this system. Okay, so I think that's enough for today. Next class, we're going to continue more about other topics.
So we have this and it can have a value of 5 volts 90. Want to leach some power off at 5 volts.